Let's begin by reviewing a concept from the previous lesson. Let G be a group element of order 6, and consider the cyclic group bracket G containing all integer powers of G. Elizabeth says the operations of Z6 and bracket G match up. What might she mean? So if you could pause the video and think about this question for a little bit, and we'll go over it in a moment. So in the previous lesson, we made this notion of operations matching up more precise by defining the following function. Function theta from Z6 to bracket G, where theta of A equals G to the A for all A in Z6. So for instance, theta of 3 would be G to the third. And then we saw that in terms of the operation of these two groups, recall that Z6 is a group under addition and bracket G is a group under multiplication. So those are the two operations of these groups. We saw that theta preserves the operations. And what we mean by that is theta of A plus B equals theta of A times theta of B for all A, B, and Z6. And that's because of the law of exponents. The left-hand side theta of A plus B is G to the A plus Bth power. And by the law of exponents, that equals G to the A times G to the B, which is theta of A times theta of B. And so this is what we mean more precisely by the operations of Z6 and bracket G match up. And it really captures the notion that addition in Z6 feels like multiplication in bracket G. We've seen that theta is not only operation preserving, but also a bijection, meaning it's a one-to-one and onto function. And that's what made theta an isomorphism. But our focus today will be on this operation preserving property of theta. So with that in mind, here is a new definition. Here's the definition of a homomorphism, which is closely related to an isomorphism, except we don't require our function to be a bijection. So as before, we'll let G and H be groups with operations star G and star H. Then a function theta from G to H is said to be a homomorphism if the following holds. The bijection part is no longer needed. So the only requirement is that theta is operation preserving, satisfying this condition. Theta of A times B is equal to theta of A times theta of B for all A and B and G. And let's do a quick review of this relationship right here. It's saying we can take a pair of elements in G, and we can either multiply them first in G and then apply theta to that product, or apply theta to A and B individually and then multiply those outputs in H. And those two processes will yield the same result. And that's what it means for theta to be operation preserving. And one remark that I like to make is that an isomorphism is a special type of a homomorphism. It's a homomorphism that also happens to be a bijection. And so every isomorphism is a homomorphism, sort of like how every square is a rectangle. But not every homomorphism is an isomorphism, just like not every rectangle is a square. And you'll see examples of such homomorphism in the classwork. But because an isomorphism is a special type of a homomorphism, that means all of the properties about homomorphisms that we'll study apply to isomorphisms as well. So please keep that in mind. Here's an important example. Let's define a function phi from the integers z to z5, where phi of a is a mod 5 for all a and z. So this is often known as the reduction map because we take an input integer and reduce it mod 5. So for example, phi of, let's say, 43 would be 3, because we're reducing 43 mod 5. The input 43 is an integer in z, and the output 3 is an element of z5. So to verify that phi is in fact a homomorphism, let's do a couple of calculations. First, we can compute phi of 26 plus 17. So we're adding these integers first in z and then applying phi to it. And so let me label this plus sign with a z to emphasize that we're adding in z first. And so that gives us phi of 43. That's the reduction map, so 43 mod 5 is 3. Now alternatively, we could apply phi to 26 and 17 individually and then add those outputs in z5. So this sum is taking place in z5. Then we get 26 mod 5 plus 17 mod 5, which is the same as 1 mod 5 plus 2 mod 5, which equals 3 mod 5. And so we see that those two processes yield the same result. So whether we add in z first and then reduce or apply phi, or reduce each of them, apply phi to them individually, and then add in z5, we get the same result. And so let me label these sums with the appropriate group in which they take place. And there's nothing special about 26 and 17 here. I'll leave it up to you to show that this relationship holds for any pair of integers a and b. And thus, we can conclude that phi is operation preserving. In other words, it is a homomorphism. Now please pause the video and work on day 17 classwork. And afterwards, we'll go over some of the questions and concepts. What's fascinating about homomorphisms is that they provide a unifying language to describe many familiar algebraic properties. For instance, we've seen this exponent law, g to the a plus b equals g to the a times g to the b, and that was described by a homomorphism theta. Theta of a plus b equals theta of a times theta of b. We also saw the reduction property, how it doesn't matter if you add first and then reduce mod 5, or reduce them individually and then add, and that was described by the fact that our function phi is a homomorphism. Here's another example we saw in the classwork. The distributive property, 6 times a plus b equals 6a plus 6b. And that was described by the fact that our function gamma is a homomorphism. Here's another exponent law that we've seen before, and that was depicted by how lambda is a homomorphism. And here is a determinant property. The determinant of the product equals the product of the determinants. That is depicted by the fact that delta is operation preserving or homomorphism. So all of these different properties that we've seen in different settings, these familiar algebraic properties, are all captured by the fact that these functions are operation preserving, and therefore they're homomorphisms. And so once again, homomorphisms provide a unifying language to describe many familiar algebraic properties. Let's talk about problem 5, where we saw a common pattern of behavior amongst these homomorphisms. In particular, if we look at the homomorphism phi, it mapped the identity element of the domain to the identity element of the codomain. And the other homomorphisms did that same thing. So here's a visual depiction of that behavior. If we have a homomorphism theta from G to H, then it maps the identity element of the domain, epsilon G, to the identity element of the codomain, epsilon H. And we often say that theta preserves the identity. So here's a statement of that theorem. We'll let theta from G to H be a group homomorphism. In other words, G and H are both groups, and theta is a homomorphism. Then theta maps the identity of G to the identity of H. In other words, theta of epsilon G equals epsilon H. And for the proof of this theorem, please take a look at the chapter 17 reading. And once again, we often say that theta preserves the identity. Let's talk about problem 7, which motivated another property of homomorphisms. So we were given a pair of matrices, alpha and its multiplicative inverse. This one was called beta in the classwork, but let's call it what it is. It's alpha inverse because alpha times alpha inverse multiplied together to be the identity matrix. Now, this equation occurs inside the matrix group G of Z10. Let's apply our determinate homomorphism, delta, to both sides of that equation. So now we have this equality in U10. But because delta is a homomorphism, we can rewrite this equation as follows. The left-hand side, using the fact that delta is operation preserving, can be broken up like this. And on the right-hand side, well, we can compute the determinant of the identity matrix, and that's equal to 1, or use our theorem from the previous slide, which said that the homomorphism maps the identity of the domain, namely epsilon, to the identity of the codomain, namely 1. And so now we have this relationship in U10. And that's telling us that delta of A times delta of alpha times delta of alpha inverse multiplied together to be 1, which means the yellow element and the green element are multiplicative inverses of each other in U10 because they multiply together to be 1. So let's dig into that concept a little bit further. So we see that delta of alpha inverse is the multiplicative inverse of delta of alpha. And let's write that down symbolically. So now we have that delta of alpha inverse right here, so that's the green element, is equal to the inverse of delta of alpha. And to write that, it's the inverse of delta of alpha. And so this bottom line, which looks like we just pulled the -1 out of the parentheses, is really a symbolic way to write down the step before it, namely delta of alpha inverse is the inverse of delta of alpha. And that was due to the computation that was done in the previous steps. And so in the next slide, let's generalize this, turn this into a statement of a theorem, and the proof will be motivated by the calculations that we just did with these matrices. Here's a general theorem. Let theta from G to H be a group homomorphism. Then theta of G inverse is equal to the inverse of theta of G for all elements little g in the group G. So our proof will very much resemble the calculations that we did with those matrices. And so let's see what we have. So we'll start with our element little g. Let little g be an element of our group G. Then we know that G times its inverse is the identity element. And when we discuss identity elements in this proof, since there are two groups, G and H, I'll be sure to label them as epsilon G or epsilon H, depending on which identity we're talking about. And the same goes for the operation, because there are two groups. I'll say star G or star H, depending on where that multiplication takes place. So as we did with the matrices, let's apply our homomorphism theta to both sides of this equation. And if we do that, well, we get theta of G times G inverse equals theta of the identity element. So let's now work with the left-hand side and the right-hand side separately. So on the left, because theta is operation preserving, theta of G times G inverse is equal to theta of G times theta of G inverse, where the operations are labeled appropriately based on where they're taking place. And then on the right-hand side, since theta preserves the identity, in other words, it maps the identity of the domain to the identity of the codomain, theta of epsilon G equals epsilon H. And therefore, we can take this equality, replace the left-hand side with this expression, and then replace the right-hand side with that expression. In other words, we see that these two expressions are now equal to each other. And that's what we have in the next step. Therefore, theta of G times theta of G inverse is the identity. And those elements are being multiplied in H. And so now I'll do a similar kind of highlighting that I did in the previous slide. We have this yellow element and the green element, and they are multiplicative inverses of each other because they multiply together to give us the identity element. In other words, theta of G inverse, that's our green element, is the inverse of theta of G, our yellow element, in H. So let's translate that into symbolic form. So we see that our green element, theta of G inverse, is the inverse of theta of G. And so that's what we have, the desired result. Once again, this last line is the symbolic version of the line before it, namely theta of G inverse is the inverse of theta of G. We'll conclude this lesson by summarizing some of the properties of homomorphisms. So we'll let theta from G to H be a group homomorphism. Then we saw that theta preserves the identity, namely it maps the identity of the domain to the identity of the codomain. Now we also just proved this property right here. Theta of G inverse equals the inverse of theta of G. And let's see what that means in the context of this picture right here. So we could start with this element little g and then invert it first in the domain and then apply theta to it. That gives us theta of G inverse. Or we can apply theta to it first and then invert that output in H. That gives us the inverse of theta of G. And what we just proved is that those two processes yield the same result. And so we'll dig much more into homomorphisms in the next lesson, but that's the end of this lesson, and I will see you next time.